Okay, good day. So we proceed to the design and analysis of compression members. So compression members are structural elements subjected only to axial compressive force. So the column being the best known type of a compression member. So actually the main purpose of column is to carry a compressive force. Then we have the three general mode of failures. Number one, flexural buckling is the primary type of buckling. So members are subject to flexure or bending when they become unstable. Okay, for the second one, this is the local buckling. Local buckling occurs when some part or parts of the cross-section of a column are so thin that they buckle locally in compression before the other modes of buckling can occurs. So for example, we have this section, for example, a wide flange. If we have a very thin flange thickness, so that is maybe prone to local buckling. So they buckle first before the entire section. Just one example of local buckling. Then number three, a flexural torsional buckling. These columns fail by twisting, or that is by torsion, or by the combination of the two. So combination of torsional and flexural buckling. Then we have the Euler Formula. For a column to buckle elastically, it will have to be long and slender. So length is a factor when it comes to compression members. Okay, so length is a factor when it comes to the slenderness of a given member. So for the Euler Formula, so let's have that as, we have that as a P is equal to the pi squared, the modulus of elasticity times the moment of inertia of the section divided by the length squared. So if we are to recall, what is the equivalent of the radius of gyration? That is the square root of the moment of inertia divided by the area. If we are to equate this one to the moment of inertia, that is the same as the radius of gyration squared times the area. So if we are now to substitute, so we have that as the P is now equal to pi squared E. A moment of inertia is the R squared times A, then to be divided by the length squared. So dividing both sides of the equation by the area, so force over area is basically a stress. Okay? That will be equal to the pi squared E. Then we are just to bring the radius of gyration, okay, as the denominator or divisor of the length squared. So that is L squared. We bring this one down. So divided by R squared. That will give us the slenderness ratio. Okay, the length over the R squared. So this will give us the Euler's buckling stress. Okay. So the pi squared E divided by L squared over R squared. Then we proceed to the column formulas. So this is for the nominal strength. So we have again the reduction factor and the factor of safety when it comes to LRFD and the ASD. So for the elastic critical buckling stress, that is the F sub E. As you can see, that is from the Euler's formula, but we have pi squared E divided by KL over R. So basically, we have KL over R is the slenderness ratio. So for the slenderness ratio, we need to determine the value of the effective length factor. Okay? Or basically, if we say effective length factor, that is the effective length factor multiplied by the length of the column, that will give us the effective length of the column. So all values will be from this table 5.1. It depends on the end supports of the given column, and we usually use the recommended values. For the flexural buckling stress, that is the F sub CR, so we have two conditions. We have A and B to determine its value. So we are to use this formulas. for our first example. So let's have an example for the design and analysis of a compression member. Okay, for our first example, I determine the LRFD design strength and the ASD allowable design strength for the 345 megapascals actually loaded member W14 by 90. So we have the properties of the W14 by 90 from our database. The area, the moment of inertia, the radius of gyration per axis. So let's have these values in millimeters. We have 25.4 mm is to 1 inch. Okay, so since this is area, so we are to square. So what will be its area in square millimeters? Okay, that is 26.5 multiplied by 25.4 squared. 17,096.74, or let's say 17,097 square millimeters. Okay, that is the area. When it comes to the radius of gyration, 6.14 inches, that is 6.14 multiplied by 25.4, 155.956, or let's say 155.96 millimeters. Then for Ry, the radius of gyration with respect to the y-axis, 3.7 multiplied by 25.4. That is 93. We have 93.98 millimeters. So if you are to observe our column, so again, this is for the first one, for the first figure, this is the y-axis. So as you can see, our y-axis is, or the moment of inertia with respect to the y-axis is our weaker axis. We have 362 inches raised to 4 for its moment of inertia. That's why it is laterally supported. Okay, just to reduce its unsupported length. Okay, then our stronger axis, this is the orientation. X-axis, we have a greater moment of inertia with respect to the x-axis. Okay, so let's have the effective length per axis. So let's have for the major axis, the unsupported length is at 10.2. Okay, so let's say that the assumed direction of buckling is in this manner. Okay, this will be the assumed direction of the buckling. This is our orientation. So again, this is the stronger axis. Okay, so let's have the effective length. Okay, for the effective length, so let's have first at the major axis. So for our major axis, so the unsupported length is 10 meters. And what will be our effective length factor? So from our table, so for the effective length factor, so what are the supports for the x-axis? So pin support on the top, and we have a fixed support at the lower end. So a pin support and a fixed support. The recommended values for the effective length factor, that will be, we are using 0.8. So this will be the effective length at x-axis, or for the major axis. So let's say this is k sub x, L sub x is equal to, we have 0.8, then multiplied by the unsupported length is 10.2 meters. So we have that value equal to 0.8 multiplied by 10.2 meters is equal to 8.16 meters. So this will be our effective length for the x-axis. Then if you are now to consider the minor axis, okay, for the minor axis, again, we place lateral supports just to minimize the unsupported length since it is our weaker axis. And our orientation will be in this direction. And it is assumed that the direction of buckling, for example, will be in this manner, per unsupported length. So let's say what will be our effective length for this section. So let's say our L1 is equal to 3.2. What will be the value of its K? Let's say K sub 1. So if you are to observe, this is a pin support or a hinge support and another hinge support. So both ends are hinge or pinned supports. So if you are to check on our table, or maybe we are just to transfer this table first. Okay, what will be the value of the effective length factor if both ends are pinned? For the recommended design or recommended values, so both ends are pinned, so we have that as 1.0. So the value of the effective length factor is 1.0. Then we have for length number 2, that is the same as the 3 meters. And also, it is a pin support, or we have pin supports at both ends. As you can see, we have both ends are pin supports. So the same that our effective length factor K sub 2 is the same as 1.0. Then for the last length, that is the 4 meters. Okay, so our length is equal to, let's say length number 3 is equal to 4 meters. What will be the value of its effective length factor if the top support or the support on the upper end is pin and the lower end support is fixed? So one end is fixed, one end is pin. For the recommended values, we have that again as 0.8. So we proceed to the computation of the effective lengths for our minor axis. So let's say this is K sub 1 L1. So K sub 1 is the same as 1.0, then multiplied by the length, that is 3.2 meters. So its effective length is the same as 3.2 meters. Okay, then for the second one, this is, let's say, the K sub 2 L sub 2. That is the same as 1.0. Unsupported length is 3 meters. So the effective length is the same as 3 meters. Okay, then we have length, effective length factor number 3, length number 3. So this is, so what is our K sub 3? So one end is pin, one end is fixed. This is 0.8. So we have the effective length factor is 0.8, then multiplied by 4 meters. So what is 0.8 of 4? That is 3.2 meters. So if you are to consider the effective length for the minor axis, the longer the effective length, it is more prone to buckling, and that is the longest will prevail. So the longest effective length will govern. So that will be what will be our value for K sub y L sub y is the longest one. So the longest one is we have 2, 3.2 meters and 3.2 meters. So our effective length with respect to our minor axis will be 3.2 meters. So we have now the effective length with respect to the x-axis and the y-axis. So we can now compute for the slenderness ratio. So for the slenderness ratio, let's say at the major axis, that is the K sub x L sub x divided by the radius of gyration with respect to the x-axis. So what is our effective length? Okay, with respect to the x-axis, that is 8.16 meters. Okay, we are multiplying 1,000 millimeters. Okay, to be in mm. Then to be divided by the radius of gyration with respect to the x-axis a while ago, we have that as 155.96 millimeters. So this value to be divided by 155.96. So is that the Rx? So we have 155.96. So let's have the slenderness ratio with respect to the x-axis. We have 8.16 multiplied by 1,000 to be divided by 155.96. So that is equal to 52.32. So what about for the minor axis? So we have that as the k sub y, let's say L sub y divided by the R sub y. That is, the longest effective length with respect to the y-axis is 3.2. This is 3.2 multiplied by 1,000 millimeters divided by what is ry? So the value of ry is equal to 93.98. So divided by 93.98 millimeters. So this value is now equal to, we have 3.2 multiplied by 1,000 to be divided by 93.98 mm. So we have that as 34.05. So when it comes to the slenderness ratio, so the larger value will govern. So if we have a higher value of a slenderness ratio, which means it is more prone to buckling. Which means that buckling may occur on our x-axis, or it is more critical compared to the y-axis. So we proceed now to the elastic critical buckling stress. So we are now to proceed for the computation of the elastic critical buckling stress. So we have that equation. For the elastic critical buckling stress, the F sub E. So F sub E is equal to the pi squared times the modulus of elasticity to be divided by the KL over R, quantity squared, or the slenderness ratio. Again, our governing slenderness ratio is the higher value, the 52.32, which means again, when it comes to buckling, the x-axis is more critical than the y-axis. So let us compute for the value, that is F sub E. F sub E is equal to, we have pi squared, the modulus of elasticity for steel is 200,000 megapascals, MPa. Then this is to be divided by the governing effective ratio, or the slenderness ratio, is the 52.32 squared. So let us compute for this value. The value of the F sub E. That is shift pi squared, then multiplied by 200,000 megapascals. Then to be divided by the governing slenderness ratio, 52.32 squared. That is 721.098. So let's say 721.098 megapascals. So for the flexural buckling stress, this is for the F sub CR. We can compute that, but before that, we need to check A and conditions A and B. So we have for the condition A. For condition A, that is if the governing slenderness ratio KL over R is less than or equal to 4.71 to be multiplied by the square root of the modulus of elasticity divided by Fy. So again, our Fy for this example, or our Fy for this example is 345 megapascals. pascals. Okay? So that's 345 MPa. Okay, so we have, Fy is equal to 345 megapascals. And the modulus of elasticity, E, for steel is 200 gigapascals. So let us check. So what is our governing slenderness ratio? That is the 52.32. So we have 52.32. Is it less than or equal to 4.71 of the square root of E, let's say 200,000 megapascals, to be divided by 345 megapascals. So let us compute. This is 4.71 to be multiplied by 200,000. Then divided by the Fy, this is 345 megapascals. So that is 113.40. So we have 52.32 is less than 113.40. So condition A is satisfied. So condition A is satisfied. Therefore, we can compute for the flexural buckling stress, the F sub CR, using this equation. Okay, so we have for the value of the F sub CR is equal to the quantity 0.658. This is raised to Fy over Fe, then to be multiplied by the value of F sub Y. So computing for the flexural buckling stress. Okay, this is F sub CR is now equal to, we have 0.658. Okay, this is raised to 0.658 raised to Fy, that is 345 megapascals, divided by the computed F sub E. That is 721.098 megapascals, to be multiplied by the value of Fy, 345 megapascals. So this is now the value of F sub CR. So let us compute. Okay, we have that as 0.658, then to be raised to Fy 345 divided by 721.098. Then again, the quantity to be multiplied by 345 megapascals. So that is 282.39. So 282.39 megapascals. So this is our flexural buckling stress. So for our LRFD and ASD design, so we are now ready to compute for the load. So basically, stress, that is the F sub CR, is equal to the load. So let's say this load will be the nominal load divided by the area. So the equivalent of our nominal load P sub N will be equal to the flexural buckling stress F sub CR multiplied by the area of the section. So we have P sub N is now equal to, what is our critical, our F sub CR? That is 282.39 megapascals, or the newtons per square millimeters. So a while ago, what is the area of our section? The W14 by 90. The area of the W14 by 90 is 26.5 square inch, or 17,097 square millimeters. So this is to be multiplied by the area, that is 17,097 square millimeters. So again, if you are to do unit analysis, cancelling square mm, the remaining unit will be in newtons. So we are to multiply 1 kilonewton is to 1,000 newtons. So we have the nominal capacity of the section will be equal to 282.39 multiplied by 17,097, then to be divided by 1,000. Is 4,828.02. So 4,828.02 kilonewtons. Then for the design strength, okay, this is now for the design strength. Okay, this is for the L, R, F, D. Wherein, okay, the value of our reduction factor will be equal to 0.90. So the equivalent of the P sub U is equal to reduction factor multiplied by P sub N. So P sub U will be equal to 0.90, then to be multiplied by 4,828.02 kilonewtons. So design strength will be equal to, this is 0.9 and multiplied by 4,828.02. This is 4,345.22. So 4,345.22 kilonewtons. So this will be the compressive design strength. So 4,345.22 kilonewtons under LR FD. Well, for the ASD, so our factor of safety is equal to 1.67. Okay, the allowable load P sub A is the nominal load P sub N divided by the factor of safety. So this is 4,828.02 to be divided by 1.67. Okay, allowable load will be equal to this is 4,828.02 divided by 1.67. And that is 2,891.03. Okay, 2,891.03 kilonewtons. So these are the design values, okay, compressive design strength for the given section for this example.